Okay, so now we can move on to CAD exercise, filter design, and verification. So we will first go about group discussion. So as you did, I think we need to reduce the time from 10 minutes to 5 minutes only. So please form a group of 3 to 4 people, as you did. Assign each person a number and discuss your overall impression of previous CADs. What worked and what was a bit confusing, and randomly chosen member will present a discussion summary. And it is recommended, encouraged to form a group chat like WhatsApp or Telegram, whatever it is, to continue discussing. So please have a discussion until 27. Okay, so sorry for interrupt. Let's have some summary of discussion session. Let me run some random number generator for left side group first, or right side group first, sorry. Oh, does this work? Okay, who is number 2? In here. So
I think CAD 4 and CAD 5 were more like straightforward, and at least it's easier for me than the CAD 4. Especially the CAD 5, I just had some difficulties in the last class, which was the easy versus this input. I just wasn't clear how that's done.
In CAD5.
CAD5.
For the
I got it done.
Okay. So do you guys have a group chat for like WhatsApp or Telegram, whatever? So if possible, please have a group chat, or you can also write a discussion forum, post about some uncertainty. So it doesn't necessarily like correspond to you don't know anything, but it's just kind of it's unclearly described. Then it's our fault. So please ask questions within your group or discussion forum post.
Yeah, but I think other than that, I didn't apply.
Okay.
Everything fine.
Okay. Cool.
Yeah.
Did you also get the overall, comparison of theoretical result and the simulation result of the CAD?
Yeah.
Okay. Cool. Yeah. Great. Thank you. Okay. Then, okay. Who is the number 5 for your group? Okay. Yeah.
So it's for my more straightforward than
Okay.
size
3.
Yeah. On that, the 4 was easier because it followed the same simulation steps as 3. And then 5 was made to be more like a tutorial, so it was more easy to follow.
Okay.
And I don't think any of us had any major issues in the CAD exercises. And one thing is that it would be nice to have the grading for the previous CAD exercises a bit sooner.
A bit sooner. Okay.
Because,
yeah.
Told me that.
Right.
Then if we repeat the same mistake in each one.
Yeah. I agree. Sorry about that. So our one of the TA responsible for grading was away for holiday. So we'll try to finish the grading of CAD3 as soon as possible. Hopefully by the end of this week, we will try. Yeah, you're right. So you're not sure whether you did in correct way, such that you don't do any same mistake again or CAD4. But that was the part of the reason why we put the theory versus simulation comparison. If you match the theory, then you did very good job. So good. Then who is number 3 in your group? Is that
Okay, let me say something. Actually, I find the CAD 5 quite straightforward, but I don't mean to that is too simple, but I think it's very meaningful. Rather than from this CAD, I think it's
better. Okay.
When I went through the big part like the design branch, I feel a little bit confused. And
Okay.
I select the frequency to draw the graph.
Okay.
Because when I choose like very low frequency like 1 hertz, and the graph the input DC voltage like shift right hand side, and it should be 0.8 as the instructions. But when I go through several times, and I find when I select the 0.1 f, and I can get the graph as the instructions.
Was it C85 or C84?
5.
5. Okay.
Maybe when you go through this part, I will focus.
Yeah. So because of time limit, we probably cannot do the C85 today, but we will definitely follow probably next lecture. Yeah, thank you. And okay, who is number 1 in your group?
Yeah. As everybody said, was much more accurate and it'll be easier to get the instruction and know what to say.
Okay, cool. Thank you, everyone. So that was my hopefully better results that I really hoped. Okay, thank you. And please don't hesitate to post any questions on discussion forum or within your group. You can also contact other person or the difficulties of going through the CAD. Okay, then let me go through CAD 3 today, and hopefully if I can also go to CAD 4. Do you see this? Oh, okay, nice screen. Right, and let me open RC filter. This was what we simulated last time. And let me clear. Tab and side like this, right? So this was a CAD exercise 3, right, for the second question. So design a second order Butterworth low pass filter using your amplifier in a unity gain feedback configuration. The filter should satisfy the following tolerance, like 100 kilohertz and the Q factor equal to similar to in a range of 0.7. And add screenshots of the designed schematic to the report. So calculate the theoretical S-domain transfer function of the second order Butterworth low pass filter with f equal to 100 kilohertz. So this can be achieved. I indeed prepare some slide. Okay, let me see. Card. Here. Oh no. Duplicate. Okay, so in previous quiz, we actually went through for this second order Butterworth low pass filter. So the answer is if you just plug in omega 0 for the 100 kilohertz natural frequency, then you can get transfer function like this. And the Q factor should be equal to 1 over square root 2. And when you set omega equal to omega 0 for this kind of general second order low pass filter, then as we went through last lecture, then it becomes to Q, and the value at natural frequency becomes to 20 times log 10 Q in dB scale. So if you understood this, you can do this part. Oh no. And calculate the magnitude of the transfer function at f equal f0 and express the result in dB, right? So the magnitude can equal to Q factor. And if you set second order Butterworth low pass filter, then the magnitude is actually equal to 1 over square root 2, which is equal to Q factor 0.7. So let's run AC and PG simulations. For the AC analysis, let me see. Let me set up again quickly. So my case was 100 femtofarad for stabilized amplifier response, and VDC, let's set 0.4 volt. Plot the magnitude and PZ. Let's set up PZ. O0. So positive output. Oh no, V out. Okay. Negative VSS. And the input source should be this one, AC source. And other things you don't need to worry about. Let's run it. So the magnitude you can plot in linear scale as well as dB scale. Okay. Right. So for dB scale, it had cutoff frequency much larger than 100 kilohertz by default last time. So let's run for 1 gigahertz. Okay. Looks like this. And in magnitude, it looks like this. So, and then pole locations and zero locations, you can just plot PZ, pole and zeros, and click the plot, and you can get it, poles and zeros here. And evaluate the AC gain at F equal 100 kilohertz. So for this kind of amplifier-based, Butterworth low-pass filter design, then let's first try to, evaluate or redesign our amplifier to match to F0 equal to 100 kilohertz. So for matching this one, so I guess if you tried to increase output capacitance, increasing the output capacitance only, then you probably get Q factor very equal to very low value as you increase capacitance. That was not the intended result, but let me first add expression of Q factor, magnitude plot, and we get this. Wait. Was 52. Oh no. We go back to 100 femtofarad. And if you click Control R, you can refresh it. Doesn't look like. Okay. Easy. Let's plot poles only. Okay, and if you put magnitude, okay, let's type point. Then this one corresponds to, conjugate complex poles, right? If you expect like calculating square root of 30 megahertz square plus 10 megahertz square, then it can be approximated to square root 32 megahertz. So for this one, maybe first value. Okay, it corresponds to Q factor. Let's take it. Q 527, right? And let me see, for the minimum value, I think if you take Y min, and probably, oh no, magnitude Y min. Okay, then it goes to natural frequency. You can double click this one again, and this way you can put F0. Okay, so Q factor is actually 527. I mean 0.527. And as we studied, TE. 75 degree. 25 degree. Okay, so let me go back to our lecture slide. This one. Okay, so the key question about CAD exercise 3, question 2 was analyzing this kind of circuit using closed loop gain format. And let's assume it has a two-pole system. I mean, for the core amplifier. Then you can plug in this open loop gain into closed loop gain equation. Then the result is like this. So this was, we went through this equation in previous lecture. I think it was lecture 5. Then the situation is quite similar that we also did today for the quiz solution. So it goes to ADC over 1 plus ADC. And you have some a bit complicated, S-domain equation. But it is, in the end, second order S-domain equation. And the thing is that it is a second order system. It can be verified or can be analyzed using 2 times zeta or 2 times, 2 zeta omega 0s or omega 0 over qs. So let's suppose that it has amplifier having ADC, DC gain equal to ZM times R out. And its 3 dB cutoff frequency is 1 over R out CL, as we did today's lecture quiz. And there was a hint. A generic amplifier open loop gain bandwidth product is GM over CL. This is exactly what we solved for today's quiz, right? And the GM is transconductance and the CL is load capacitor here. And let's assume that it has many poles as we have in our analysis. If you plot the pole zero analysis, then there are some poles, right? That means it has multiple poles. And then you can also plug in into open loop gain, into closed loop gain. Then there can be some high order S domain equations, but still you can have a DC form. And it can be organized into like first pole, second pole, third pole, and so on and so forth. But if you approximate this circuit as a two-pole system, as we saw in our PZ plot, there was a 2-pulse at the low frequency, which is a complex conjugate, then we can approximate, okay, our amplifier has a 2-pulse only. In that case, we can, approximate our closed loop gain as well, exactly same as previous case, which is assuming to 2-pole amplifier. So now we can analyze this kind of closed loop system as we went through for the analysis of, damping factor versus base margin in lecture 2 and lecture 3. So the key thing was, if you set base margin in a range of 65 degree to 70 degree for this amplifier, then you get Butterworth response. That was the main factor. So you can design this amplifier having base margin, let's say 55 degree. Okay, this was what we designed. Okay, let me go back to our case. So now its base margin is 75 degree. So let me decrease this value, CL, to match as much as possible to 65 degree base margin. 67, what about 40? Yeah, it's a 65 degree. And in the Q factor, it doesn't look like changing much. Q factor 2, 5 to 7. What is happening? Right. So what I meant was you can approximate your amplifier having 2-pole system, and the high order poles can be approximated as a high frequency. So the main question was approximate your amplifier using 2-pole system like this, closed loop. Anyway, what is wrong with this? Let me see. Log. Yeah. So I think there was some calculation incorrectness. We can do it again. Magnitude. Magnitude. Yeah, it says 0.738. Magnitude and first value. Wait. Okay. See here, and let's remove this one. Oh, okay. It was fixed as a 0.5277, which was incorrect. And F0 was correct. Okay, so Q factor is 0.7, right? 73. And this is within the specification, right? 0.73 is within 0.65 and 0.75. But our cutoff frequency, I mean the natural frequency here, F0 is much higher than 100 kilohertz. So if you just increase CL to decrease the F0, then you lose Q factor specification. So in this case, the other way around is only way is controlling GM here, GM. That was the hint. And let me go back to our slide. To realize decreasing GM, as we went through in lecture 5, you can either control VGS minus pre-threshold or control ID. So to decrease GM, you can simply decrease the bias current. Then your amplifier becomes slower and slower because our bias current is very small amount. So that was the key point. So let me reduce this one to maybe like 1 nano, because our megahertz, I mean our cutoff frequency, sorry, our natural frequency is as high as 42 megahertz. And let's see what happens. Yeah, then F0 becomes to 153 kilohertz, and the phase margin and Q factor. The phase margin is slightly increased, but we can control CL. Anyway, let me control this one to maybe like 0.7. Let's see. Okay, very closer. And what about 500 pico? Okay, 82. Maybe we can control this capacitance 30. Then we can decrease phase margin. Yeah. Then we can further decrease to 0.5. Let's say 20. Yeah, nicely matched to almost 100 kilohertz. And the phase margin is 65 and Q factor is 0.75. So we can slightly increase bias current. No, increase the capacitance. 0.2 maybe? Okay, then 99 kilohertz, right? And the phase margin is 66, and the Q factor is within specification. So now it is all set. So from the PZ plot, verify the filter's low frequency pulse here, near cutoff frequency. So let me plot pulse. Now you can find out that its conjugate, complex conjugates are here. And those are low frequencies, and it is still like lower than other frequencies. So we can approximate this system as a two-pole system, like this way. And low frequency poles are here, right? Because it is closer to 100 kilohertz. And calculate the theoretical magnitude of pulse, which goes to natural frequency. So we are already doing here. And from the PZ plot, verify your filter's Q factor. You can do manually by calculating S1 plus S2, which goes to only the rear part of pole. But I'm just calculating Q factor using calculator. And fine-tune your circuit such that filters F0 and Q satisfy the target tolerance. We already did, right? So verify your design against the theory using Python or MATLAB. Plot and overlay AC gain and the transient step response. Okay, so let me plot AC gain. All right. Okay, and I can prepare your notebook here. So you can go to our GitHub of CAD exercise. Let's name is 83. Yeah, and we get it. And previously we used the Excel for the CAD exercise, but I found out a better format, which is TSV format. So you can export this result here. Let's copy. And let's say CD3 TSV. And copy, paste. Let me call it as a CD3 as a AC, CD3 AC. Then CD3 AC, TSB. So TSB means that tap separated values. So those values are separated by taps, tap. And we can, import this data using Python, pandas. And so we defined data frame 0, first column and the second column. Let's run the simulation. What is happening? What has no... Oh, there was a mistake. Read. Okay, good. And we need to run the simulation for the Q factor equal to 1 over square root 2. So let me see, where is it? Q factor. Let's call theory or worse. And where is a Q factor? Oh, here. 7. Yeah, then it matches quite well, except for some high frequency things. So plot fx. Let's rearrange this one like this way. Yeah. So we are facing the situation that this part around the natural frequency, it matches quite well, but it goes to different shape, and it has a flat band, right? That was the tricky part that I asked to go through. And yeah, so for the step response, you can do a similar way. Copy, paste here. And let me quickly run the step response. Okay. And the transient. Reset step. All right, step. And it was 20 micron. So let's run 20 micro. And let's see what happens. Transient. Okay. So I applied small amount of step 15 millivolt with the DC voltage equal to 400 millivolt. And the output is here. So we can export this data. CD3 step ESP. Okay, so let's run the basic simulation first, and Q factor for a worse, and the Q factor equal to 0.7. It looks like this. This is a theory. And let's say step. And here. Then there are some deviations for the DC starting point, right? So you need to manually match it. So for this one, 416, and the end point is 463. So 416, 416, and what is the magnitude? Magnitude is 47 millivolt. Magnitude is 47. Yeah, then it matches quite well. I mean, if you want to match as close as possible, then you need to manually adjust this F0 and the phase margin, for example, controlling capacitance 22.5 or 22.55, something. But I think this is pretty much good enough. So let's see. Let me go through the remaining part. So if your amplifier filter shows a flat stop band attenuation, this is our case, right? Attenuation here. Then discuss the reason for this. The region was already discussed in CAD exercise 2 live demo. You can watch the YouTube video again, and proposed a new amplifier design to improve the stop band attenuation by more than 20 dB compared to the baseline. So sorry for having delayed lecture. So let me quickly go through. So this is a source degeneration. That was the key part of a solution. So you probably learned from Basics of IC Design course in lecture 3. By using this kind of source degeneration, you can actually make our transconductors 1 over GM plus R. So basically what it does is that we can add resistance at the source node. So our problem was indeed as I introduced in CAD exercise 2 live demo, that there was a porosity cap CGS that makes V input to be short-circuited to V in. That was the problem. So if you put source degeneration register here, register and register, then you can at least make the short circuit current very, very small amount that can avoid, making additional zero. So that was a bit tricky part. But if you couldn't make this possible, please don't be too much, unsatisfied, because it was intentionally designed to be very challenging. And now I understand that was not that much helpful for our daily life. So I would not consider adding that kind of tricky questions in the remaining CAD exercises. For example, CAD exercise 5 or 4. So let's add, for example, 100 kilo ohm and AC dB as a reference. This is a previous result, and if I run AC simulation again, then you can see that something is happening, right? Going down by adding resistance here. So you can increase the resistance value. So it adds some sort of, some sort of pole frequency that is associated with the porosity capacitance. So if you increase to 1 mega ohm, then let's see what happens. Then it goes to like this, right? So if I increase to 5 mega ohm, it goes like this. If I increase to 10 mega ohm, okay, so you can increase this resistance more and more and more to, improve the stop band attenuation by more than 25 dB. And then we already have seen that our filter response was quite close enough to the theory. You can see that is, this natural frequency part doesn't deviate that much, right? So this part can be dragged down more than 20 dB. And you can also verify step response and the AC gain by comparing theory and your simulation result. So this was the CAD exercise 3. Sorry about it. Unfortunately, we couldn't go through the CAD 4, but I will try to make sure CAD 4 and 5 by the end of next lecture, next week. So we can have short break for 5 minutes. And the quiz is waiting for you. Thank you.